My name is Diana Turmahan and I'm the undergraduate research assistant at Institute of Smart Systems and Artificial Intelligence. And this is the first part of the model training and evaluation part of our comprehensive tutorial series on speech command recognition. In preceding tutorials, we discussed the process of acquiring training and validation data, such as generating synthetic dataset using TTS technology, scrapping speech corpus dataset, and also talked about collecting real data using Telegram bot for testing purposes. In today's tutorial, our primary focus will be on model training and evaluation for speech command recognition. The process of training model involves three key stages to ensure optimal performance. They are dataset splitting, model training, and model evaluation. Each stage is essential in building accurate and robust models, and let's explore each stage in detail. The first step is dataset splitting. To develop the reliable models, it's essential to divide the available dataset into three subsets: training, validation, and test set. The training set is used to train the model and adjust its parameters. The validation set is used to fine-tune the model and select hyperparameters. The test set is used to assess the final performance of the trained model. Significant percentage of data, around 60 to 80, is allocated to the training set. Around 10 to 20 is allocated to the validation set, and the same amount for testing. The second step is model training. The training process involves optimizing the model's parameters to minimize the chosen loss function. This is typically done through techniques like a gradient descent, where the model iteratively adjusts its weights based on the previous training data. And finally, evaluating the model performance using suitable metrics and techniques ensure its reliability. Before training a model, it's crucial to choose an appropriate architecture based on the problem at hand. For our task, the keyword MLP model was utilized for speech command recognition, and thank you for authors to providing for this model. This model was chosen due to its high accuracy, which is 97.56% on the test set of Google Speech Command Dataset version 2, which is comparable to state-of-art models such as Keyword Transformer. Most importantly, the Keyword MLP model offers enhanced parameter efficiency with 424,811 parameters, making it suitable for deployment on edge devices with limited computing resources. Dataset splitting is a crucial step in the development of models. It involves partitioning the available data into subsets to facilitate training, validation, and testing, as we said before. In this section, we will explore specific details of dataset partitioning of processed Kazakh Speech Corpus 2, synthetic TTS, and Kazakh Speech Command dataset. The synthetic TTS and processed Kazakh Speech Corpus 2 datasets were split into training and the validation sets. The processed Kazakh Speech Corpus 2 dataset was partitioned in a manner that ensured augmented samples in the training and validation set were derived from distinct, non-overlapping samples. The training and validation set contains 74,891 and 6,474 samples correspondingly. In generating synthetic TTS dataset, we used the voices of 5 speakers, 3 females and 2 males. Consequently, the data generated by 2 males and 2 females were designed as training data, while the remaining female voice was assigned to the validation data. As a result, the synthetic training and validation set consists of 75,600 and 9,450 samples, respectively. And the real-world collected dataset, which is called Kazakh Speech Command dataset, was employed only for model testing, which consists of 3,623 samples. Now let's take a closer look on how the training is proceeded. We employed 2 distinct model training strategies. The first approach entailed training from the scratch with the random initial weights, while the second involved transfer learning. We trained the Keyword MLP model on the Google Speech Command dataset version 2 using default hyperparameters. The model achieved 94.58% on the training set and 97.39% on the validation set and 97.5% on the testing set. The results were close to the ones presented in the original paper. In the both training strategies, the model was trained on the synthetic CTS and the processed Kazakh Speech Corpus 2, on a combination of these two datasets. In all cases, the model was tested on the collected real-world dataset. The model was trained on the NVIDIA A100 GPU for 100 epochs with a batch size of 256. The augmentation rates were tuned for each training strategy. Now let's discuss the outcomes. The table demonstrates the performance of the model on different collections of data. The model trained solely on synthetic TTS dataset achieved approximately 90% accuracy on synthetic training and validation set, and 70% on the real-world test set. Employing transfer learning further enhanced the accuracy for each set as well as for the test set, achieving 82.5%. Although we can generate a large-scale synthetic dataset, the underlying source is still 5 speakers' voice. Therefore, the model tends to overfit quickly. To address this issue, we applied spectral augmentation methods such as time masking and frequency masking during the training. When the model was trained using combination of synthetic TTS and processed Kazakh speech corpus 2 dataset, it obtained 87.39% accuracy on combined training set and the same on the validation set, and 85% on the real-world test set. Employing transfer learning further enhanced the outcomes, with the model achieving 88% on the accuracy training and the same on the validation set, and 89% on the real-world test set. This result indicates that synthetic TTS dataset and processed Kazakh speech corpus 2 dataset complement each other, leading to a more accurate model. The classification results for the best performing model is presented in this table, highlighting 5 most frequently confused commands in bold. For instance, the model often mistakes with the command bird, which is cos, for the command on, which is cos, in 15% of cases, and vice versa in 12% of cases. The main factor for this confusion are short lengths and similar of these commands, as they differ by a single phoneme. Additionally, the model confused on house, which is y, and dog, which is it, in 35% of instances. The primary cause for this confusion is that both commands are quite brief, consisting of only 2 phonemes, and pronunciation of house, which is y, in Kazakh language can be challenging even for native speakers. Consequently, many people pronounce this word differently, leading to model confusion. Furthermore, the model often misclassifies write, onga, and read, oqa, due to similar sound of these words. As we have discussed the results of the model training, now let's move to the coding demonstration to see it in detail. First, go to the eScience GitHub page. After, search for the Kazakh speech command dataset. Then clone the keyword MLP directory in this repository. After that, download the necessary dataset separate for training, validation, and testing purposes. The testing dataset, which is called Kazakh speech command benchmark dataset, can be downloaded from the Google Drive. After, to train the model on the synthetically generated dataset and scrapped Kazakh speech corpus 2 dataset, download the combined dataset from the Google Drive. After downloading necessary directory and the dataset, proceed by following instructions provided in the README file of the repository. Let's have a closer look at the structure of the dataset. The training and the validation dataset is a combined version of the synthetic TTS dataset and processed Kazakh speech corpus dataset, as it gives the most accurate performance, and it's kept in the folder KSC TTS data. In the if open, the dataset consists of a large number of audio files, each representing a spoken command. The dataset organized into folders, with each folder representing a specific command, a keyword, for example, backward, bed, bird, cat, and so on. If you open one folder, there is a collection of the audio files corresponding to this command. The testing dataset, which is kept in the data folder, keeps the same structure. Let's move to the coding part of the tutorial. First, make sure that we are working on the keyword MLP directory. Then, start by installing all required libraries and packages using pip install requirements.txt. Then, unzip the all dataset needed in the current directory. Before proceeding to training phase, please set up your OneDB environment by setting up OneDB API key variable. OneDB refers to weights and biases, a machine learning experiment tracking and visualization platform. The training procedure uses for tracking checkpoints and visualizing the changes in loss and accuracy over the number of epochs. This will help determine the optimal hyperparameters. After, run the Python train.py. This command line executes a Python script named train.py with specific command line arguments, which is config file. This configuration file appears to contain settings and parameters for a speech command recognition task, which we can visualize here. First is data root. Data root specifies the root directory for dataset used for training, validation, and testing. After the training list, validation list, and so on, these parameters define the file paths for the list of audio files used for training, validation, and testing respectively. The label map. Label map, this points to the JSON file that maps labels to numerical values of the classes. After the AXP session contains parameters related to the experiment setup, such as enabling 1DB account for experiment tracking, the project name, the experiment directory, and other settings. The HParams, this section includes various hyperparameters for training process, such as path to the checkpoint to restore the model, the random seed, batch size, and number of epochs. After audio specifies the audio parameters. Model specifies architecture and the configuration of the model used for TTS, including the parameters like the type of the model, input resolution, patch resolution, and number of classes. After we have the optimizer. Optimizer used for training the model, specifying the type and its corresponding arguments. Next, execute the inference file to make predictions on the testing data. The first argument specifies the same configuration file as it's in training. The second argument specifies the path to the checkpoint file, which is the best PTH used for loading the trained model weights, which was saved after the running training script. The next specifies the input directory where the input data is located. After the indicates output directory path where the generated outputs or results will be saved. Then the second is indicates the label map file used for mapping predicted label to corresponding values. Device CPU specifies that CPU should be used for running inference process instead of GPU acceleration. And the last one is indicates the batch size. All predictions after running the inference.py will be saved in the JSON format, which is preds.json. And finally used results.py script to assess the model's performance on the testing data. Pass the JSON file containing all the predictions used for generating results, analysis based on those predictions by calculating metrics such as F1 score, precision, recall, and support. And here the results that should be appeared. Now let's test our model on one audio. So we first pass the audio pass. Then we run the inference.py for only one audio. Then it saves its output in preds.json. Then we read this preds.json file and it gives the backward. Let's check if it's correct. So run the audio that we have downloaded and listen. Artka, yes, this is correct. Artka means in English backward. So our model succeeded in extracting text from the audio. And that is the end of our tutorial, and thank you for your attention.